So the chain rule is a way to differentiate what we call composite functions. So if you think about a composite function, it's the idea or the concept of having a function inside another function. When you have FOIL and you have like x squared plus 2 inside parentheses, and then you square that whole function, that's actually a composite function. It's two functions that make up a whole. So you could rewrite that as f and g's. So what I mean is if you had x squared plus 2 and you square that whole quantity, you could say f of x is equal to x squared plus 2 and g of u is equal to u squared. And then if you use function composition, you can combine the two to give you this. So that's where you'd say, oh, well, f of g of x is, and that's when we would plug in one function to the other or vice versa. So function composition is an application of the chain rule. So we have the statement that f and g are both differentiable. And f, which is a capital letter now, equals f of g, is the composite function defined by capital F. Then f is said to be differentiable, and f prime is given by the following product, where it's the derivative of the outside times the derivative of the inside. So if I were to do this problem over here, the outside function would be the u squared. So what's the derivative of u squared? What's the derivative of f? So here, when you do this, the outside function is the f of x, or rather the g of x, and the inside function is the f of x. Oh, I wrote it backwards on here. Sorry, guys. Because you're putting f into g, so that you have x squared plus 2 squared. So it's kind of that's kind of backwards from what's up here, in the sense that that would be g prime, f of x, f prime. Leibniz notation is a little bit different, and that's almost what I was getting at with this. It's y equals f of u, and u equals g of x, are both differentiable. Then dy dx equals dy du times du dx. This is where I said it's important to know what this notation represents, where this is saying it's the derivative of y with respect to u. So derivative of y with respect to u times the derivative of u with respect to x. And what would you say happens here? If these represented variables, you would say, oh, the du's cancel each other, and you get dy dx, which is our ultimate goal. So there will be times where we are using this Leibniz notation to cancel out certain derivatives where variables don't match. In effect, this rule tells us how to differentiate from the outside in. It's the opposite of what we normally do, right? When we learned math way back in the day, we always said parentheses first. Absolute values, you did the inside first. Well, the chain rule is the opposite. It's outside in. So you do the outermost function first and work your way in. So if it's f of g, we're going to derive f, not touch g, then times it by the derivative of g. So it's the derivative of the outside, leave the inside, times the derivative of the inside. So here, it's simple or helpful to rewrite f of x as an inside and an outside. So what would the outermost function of f of x be?
Instead of 1/2?
Yeah, it'd be the square root of x, right? So if you're rewriting it using the notation above, then we could say, all right, f of u is equal to the square root of u, and u is equal to 3x plus 2. So outside function, inside function. What's the derivative of the square root of u? Good. What's the derivative of u? So now what we do is we put the u after this. So we have f prime of u times u prime. So you're going to get 1/2 u to the negative 1/2 times 3. Plug back in my original u. So we're in terms of x's instead of u's. And we get 1 times 3 over the square root of 3x plus 2, or 3 over the square root of 3x plus 2. Again, that's just one way to do this. We're going to talk about notation and simplification.
Is there another 2 on the bottom? Yeah, why is that going?
Oh, I just forgot to follow it on. Thank you. I forgot my 1/2. Just write in a little tiny thing. So again, it's outside times inside. Once you get really good, you can eliminate these steps. You're not going to write them forever. They're helpful now to see the two functions. As we get better and better, you're going to just start taking the outside derivatives times the inside. So like, for example, what is the what's wrong? You need me to go back.
Yeah.
In the next problem, what's the outer function? Well, it's the function outside the parentheses, right? So outside the parentheses is a square. So the outside function is the square. So what do you do with the square? The power rule says we bring down the power. And you subtract 1 away. So ignore the 2x plus 4. Treat it like you did the x. Treat it like x squared. So you get 2x times 1. Times, what's the derivative of the inside? The derivative of 2x plus 4. So again, outside times inside. Is that confusing, or do you like the u's?
This is better. The u's were like evil.
So you get 4, 2x plus 4. But again, can I distribute that because that's a power of 1? So we like our answers to be as neat as possible. So we get 8x plus 16.
I don't mind the u. No, u okay.
Okay, so you want to see the u?
Keeps it together. Where do you get that from?
Okay, ready? Let's call this two different functions again. Let's call the x part u. So you get u equals 2x plus 4. So derivative of u is what?
2.
Okay. Let's call the outside function u squared, because this would be representative of 2x plus 4. So you get u squared. So it's the derivative of u squared.
2u.
Okay. So now the rule is that it's f prime of u times u prime. So you get f prime u times u prime. So we get 2u times 2.
4u.
Yep. And then what was u?
2x plus 4, so
That 2 here is the same as this 2 there. As I said, if the U's work for you, then use the U's. And I don't mind doing the problem both ways. You have to pick what works for you. Some people, that was not a. Okay. Yes, I was being funny.
You said you. I don't know. It's a really common word, but it's so funny.
It's all good. So, I will say the chain rule with the product rule gets a bit messy.
It's terrible.
So, this is a problem where I would rename my parts. So what I would do here is I would say, okay, this right here represents my U. So you get U is equal to 2x plus 1. What's the derivative of that? 2, right?
Use B on the other one.
Exactly. So you're going to change the variable for the other part. So I would say V is equal to x cubed minus x plus 1. And then what's the derivative of that? Good. So now this is why the U's and the V's are somewhat helpful. Because we can rewrite f of x as u to the 5th times v to the 4th. Remember, u and v are functions. So what's the product rule say? It says the first times derivative of the second. So what's the derivative of 4v? Or v to the 4th, rather. Oh, man. 4v. Times v prime. Because it's a chain rule. What? Okay. Plus the second. So what was the second function? Times because these are functions raised to an exponential power, so they're the chain rule. So they're like this. They're like this example here. F prime of u is the function times u prime. So the rule is the function, the derivative of the function times the derivative of the inside function. Yes. So I know it's hard because you see u and v's as variables, but it's almost like that homework problem we had with 23 and 24. U and v's aren't variables, they're functions raised to exponents, which is even trickier. All right. So, what do you notice about the u's and the v's? If u and v were variables, you have u to the 5th plus u to the 4th. Same base. How many in common? There's 4 u's here, and there's how many here? So wouldn't my math be a little easier if I brought 4 out as a GCF? How many v's are here and how many are here? So wouldn't my math be easier if I brought out 3? All right. What is left behind? If I took 4 away, I have how many left? If I took 3 away, how many are left behind? 9. But there's still a 4 and a. Okay. Okay. How many did I take away? Okay. How many did I take away? So what's that leave behind? The 5, right? Yes.
Really, 5u prime. Do you have to close up?
I'm not done yet.
Bracket.
My bracket's not closed until right now.
We have to plug stuff back in, or?
Yes.
Oh, boy.
So now you plug it all back in. So I don't know what color to plug it back in. U to the 4th becomes 2x plus 1 to the 4th. V cubed becomes x cubed minus x plus 1 cubed. Bracket for u, which was 2x plus 1. V prime, which is 3x squared minus 1. Plus 5 v u prime. Oh, you think you're done?
You're not done?
Oh, algebra.
Real algebra.
Algebra.
Hold on. Wait.
You have to distribute and get it down to single term polynomials.
No.
Yes. So I FOIL this. So you don't know. So what I would do, you don't have to know, you're not going to do anything with these. You're just going to simplify the bracket.
Okay.
But what I would do is I would distribute that 4 into one of the parentheses.
Yeah, that's my idea.
So I would rewrite this as 8x plus 4 and then FOIL. So you have 8 times 3, which is 24x cubed. 8 times negative 1. 4 times 3. And 4 times negative 1. I'd take the 5 and the 2 and make a 10. And then distribute my 10 in. And remember, these two sort of just tag along. They're along for the ride right now. So your final answer (24 and 10) combined.
Okay.
12 is alone.
What are you? But what's confusing me is when the second time you start the derivative, because you're saying that's all f of x.
Oh no, this is F prime. Okay. 12x squared. 8 and 10. Yeah, and then the 4 and the 10. Sadly enough, these are all actually divisible by 2. You could have GCF down 2. Like way up here.
And you stop there? Okay.
That's the answer.
All right, and the very last example we're going to look at is a chain rule with a quotient rule. So in order to find our derivative, we're still going to apply the quotient rule. So it's Hody high So now it's just the derivative of the top using the chain rule. So 4x minus 1, take 1 away, you get 3. Derivative of x minus 1 is 1. So Hody high minus high d ho. Derivative of the denominator, 5x squared plus 2x times derivative of the inside, and that's to the power of 4 because we took 1 away, 2x plus 2. So Hody high minus high d ho all over the denominator squared. So 5 to the squared becomes 10. And then what we're going to do is just clean this up algebraically. So what you'll notice is that over here I have 3x minus 1 cubes. And over here I have 4. So I'm going to bring out x minus 1 cubed. And then over here I have 4x squared plus 2x. And over here I have 5. So I'm going to bring out 4. So that leaves me with 4x squared plus 2x, because the x minus 3's all got pulled out, minus 5x minus 1, because 1 stayed behind, all 4 came out, and then 2x plus 2, all over x squared plus 2x to the 10th. And then what you should notice is that I have 4 and I have 10. So you can take 4 away, and that leaves you with 6. We're going to distribute our 4. So that gives me 4x squared plus 8x. And I'm going to FOIL and distribute here. So that would give me 5x minus 5 times 2x plus 2. And then that gives 10x squared minus 10x plus 10x minus 10. And then we have x minus 1 cubed, 4x squared plus 8x, minus 10x squared plus 10, because the minus 10x and plus 10x cancel, all over x squared plus 2x to the 6th. Combining one last set of like terms, we get x minus 3 cubed, negative 6x squared, plus 8x plus 10, all over x squared plus 2x to the 6th power.